Hello, everyone, and welcome back to Vision Unleashed 10 Breakthroughs Shaping the Future of Computer Vision. I'm Ramas Iyer, and today we are on episode 7 Bridging Language and Vision, where we unpack CLIP, the contrastive language image pre training approach that actually taught models to link pictures and words at a massive scale. Joining me as always is Dr. Sukant Khurana. Great to have you here, sir.
Thanks, Ram. Clip is one of those breakthroughs that made zero shot understanding truly practical. It changed how we think about teaching machines to see with language.
Yes, so let's start at the beginning. OpenAI trained clip on roughly 400 million image text pairs scrapped from the web. Instead of training on fixed labels, Clip learns to match each image with its natural language caption and to distinguish it from all other captions. So, how did that contrastive objective reshape vision tasks?
Yeah, that's very important. The contrastive objective is elegant. Each image embedding is pulled closer to its matching text embedding and pushed away from everything else in a shared latent space. That means after training, you can ask Clip to classify images by simply encoding your class names as text and finding which text embedding is closest to the images. No extra fine tuning is required.
Rather than designing specialized classification hits, you define a prompt let's say, a photo of a hot dog or a diagram of an aeroplane, encode those traces and let Clip pick the best match. I have even seen demos where it distinguishes between let's say, an arc and a bridge with surprising accuracy, even though neither label was in a fixed training set.
Exactly. The flexibility is powerful. For example, if you need to categorize medical scans into pneumonia versus healthy lung, you simply encode those text prompts and use Clip as a zero shot classifier. No need of hundreds of labeled x rays.
Yes, sir. I have been working on contrastive learning, but in a self-supervised learning sphere, experimenting with SimCLR and all. But walk us through Clip's architecture. How do the image and text parts come together?
Okay. Clip has two encoders, one for images, often a Vision transformer or ResNet, and one for text, typically a transformer from language modeling. Both encoders output fixed length vectors. During training, you gather a batch of n image text pairs, compute all n image embeddings and n text embeddings, then apply a symmetric contrastive loss. So each image is encouraged to pair with its correct caption and repeat the other n minus 1 captions and vice versa.
Yes, that symmetric loss kind of elegantly balances both modalities. And because the text encoder sees raw language, you can craft hundreds of different prompts at interface time, like a sketch of a cat versus a photograph of a cat to bias clips focus. I've used that trick to switch between line drawing and photo style classifications in a single model to be prompts.
Yeah, prompt engineering indeed became a new art by changing our test text descriptions, adding adjectives or context. You guide Clip's interpretation. That's a major reason Clip laid the groundwork for models like DALL-E and Stable Diffusion, where text conditioning drives image generation.
Exactly, sir. What about a real world impact? Where have you seen clip shine at its best, sir?
So there are one standout is content moderation. Instead of retraining classifiers for every new category of harmful imagery, you can zero shot filter by encoding phrases like graphic violence or hate symbol or scanning user uploads. Another is wildlife monitoring. Camera trap images in remote jungles can be sorted into elephant, tiger, or nothing here with minimal or no labeled examples.
Exactly, sir. So those are some use cases, and I have also seen like clip used in interactive art apps, where user type a poem or a phrase and the system fetches images or visual motifs that match the text in real time, thanks to clip's giant space, right, sir?
Yes, robotic teams leverage CLIP for open vocabulary object recognition. Instead of bounding the robot's world to a fixed set of object classes, you can ask it to fetch the red mug or the rectangular box on the fly simply by encoding those instructions.
Truly, sir. Despite its kind of strengths, Clip has challenges like dataset bias, robustness to adversarial prompts, and occasional confusions on fine-grained categories. So, how do researchers address those at present time?
Approaches including filtering or rebalancing the web scrape data to reduce underrepresented groups, refining prompts to mitigate bias, and combining CLIP with self supervised adapters that fine tune on domain specific data while preserving zero shot flexibility. Also, ensemble prompt strategies, averaging over multiple phrasings, can improve stability and accuracy.
Yes, sir. So, looking ahead, what's the next frontier for vision language models according to you, sir?
Scaling to video and 3D, integrating spatial temporal cues, and grounding language in action. So models only recognize objects by name, but also follow instructions like pick up the blue cube and place it on the yellow platform. Clip success proves that joint embedding is powerful. The next wave of embedding vision, language, and next wave is embedding vision, language, and action together.
Fantastic insights, sir. So, thank you, sir, for unpacking clip and how contrastive pre-training bridges language and vision. Next time on Vision Unleashed, we'll dive into dreams from text, exploring how DALL-E 2 and Stable Diffusion's text-to-image revolutionization. So, you won't miss that.
Looking forward to it, Ram.
Thank you, sir. So, thank you for listening, all. If you enjoyed this episode, please subscribe, like, and share. I'm Ramasaya. See you in episode 8.